Good day, people. Today we will be seeing formulas for any mean when inserting q means in between two terms in a sequence. The formulas to be proven below will work for getting any single mean when we insert q means between two terms in any sequence. These formulas are m sub p is equal to quantity q minus p plus 1, a sub 1, plus p a sub n all over q plus 1 for your arithmetic mean. M sub p is equal to the q plus 1, if that's how you read it, root of the product of a sub 1 raised to q minus p plus 1 and a sub n raised to p for your geometric mean. Finally, we have m sub p is equal to the product of quantity q plus 1, a sub 1, and a sub n all over q minus p plus 1 times a sub n plus p a sub 1 for your harmonic mean. So first, let's start with the arithmetic means. Given two terms a sub 1 and a sub n, where a sub n is equal to a sub 1 plus quantity n minus 1d, we prove the base case of inserting one arithmetic mean between those two terms. Since one term is inserted between a sub 1 and a sub n must be two terms away. So n is equal to 1 plus 2, 3. So a sub 3 would be equal to a sub 1 plus quantity 3 minus 1d, or a sub 1 plus 2d. To get the arithmetic mean of a sub 1 and a sub 3, we simply add them and divide by 2. As shown here below, we have m sub 1 is equal to a sub 1 plus a sub 3 all over 2. We then define a variable q representing the number of means to insert between a sub 1 and a sub n. The sequence has n terms: a sub 1, q means, and a sub n. We are left with q terms if we remove a sub 1 and a sub n, so q would be equal to n minus 2. In the earlier example, we illustrated the base case q is equal to 1. The last term was a sub 3 as we inserted one mean, proving q is equal to n minus 2. And the denominator was 2, which is q plus 1. We then define a variable p representing the mean's position. Basically, the formula is for getting the pth mean when inserting q means. To get a better explanation, let's illustrate the case where we insert 3 arithmetic means. Since q is 3, add 2, so n would be equal to 5. So to find how p works, we first get the arithmetic mean between a sub 1 and a sub 5. So we are inserting 3 arithmetic means. This mean is the second out of 3 to be found. The first and the third, we'll find those later. So there you have it. M sub 2 is equal to a sub 1 plus a sub 5 all over 2. We then get the arithmetic mean between a sub 1 and m sub 2 to get m sub 1 and m sub 2 and a sub 5 to get m sub 3. Recall that m sub 2 is equal to a sub 1 plus a sub 5 all over 2. So here, we had to rewrite m sub 2 as a sub 1 plus a sub 5 all over 2 so we can make things a bit quicker. Multiply a sub 5 by 2 over 2, multiply a sub 1 by 2 over 2, then add those two fractions together. For m sub 1, we'd get 3 a sub 1 plus a sub 5 all over 2, and still over 2. Then for m sub 3, we get a sub 1 plus 3 a sub 5 over 2, all over 2 again. Since this is a complex fraction, we can simplify it by multiplying everything here in this numerator by 1/2. So we'd get m sub 1 is equal to 3a sub 1 plus a sub 5 all over 4. And m sub 3 would be equal to a sub 1 plus 3a sub 5 all over 4. We can then rewrite m sub 2 is equal to 2a sub 1 plus 2a sub 5 all over 4, and observe the coefficients of a sub 5 always equal p, because earlier we saw that m sub 1 is equal to 3a sub 1 plus a sub 5 all over 4, and m sub 3 is a sub 1 plus 3a sub 5 all over 4. So m sub 1, the coefficient of a sub 5 was 1. M sub 3, the coefficient of a sub 5 was 3. Either way, the means positions correspond to the coefficient of a sub 5 here. And the denominators and the sum of the coefficients of a sub 1 and a sub 5 always equal q plus 1. Earlier, we saw that the denominators for those three means were all 4. And for the numerators, the coefficients 1 plus 3, 2 plus 2, 3 plus 1, all of those equal 4. We then get the equation where x is the unknown coefficient of a sub 1. So basically we have q plus 1 is equal to x plus p. We solve for x by subtracting p from both sides. So the coefficient of a sub 1 is always equal to quantity q minus p plus 1. From what we observed in the previous examples, the general formula for getting the pth arithmetic mean when inserting q arithmetic means between a sub 1 and a sub n is... there you have it. M sub p is equal to quantity q minus p plus 1 times a sub 1 plus p a sub n all over quantity q plus 1. Again, you can pause the video at any point since you might need to process all that information. Right. Now for geometric means. Again, this will actually follow very similar logic to arithmetic means. However, whatever we added in or any additions in the arithmetic mean become multiplications here. Whatever multiplications we did in arithmetic become exponentiations here. And whatever divisions we did there in arithmetic become radicals here. So given two terms a sub 1 and a sub n is now a sub 1 times r raised to n minus 1. Again, we insert one geometric mean. The logic. So here, the geometric mean, multiply the two, get the arithmetic mean of their exponents, then we can rewrite a sub 1 as a sub 1 raised to 2 over 2. Then they both get under the radical sign. Now we have m sub 1 is equal to square root of a sub 1, a sub 3. Again, we define the variable q. Yeah, the logic was very similar, except quotient has now become the index of the radical. If you do not see an index of the radical, it's implied to be 2, since square roots are commonly written without their indices. Again, we define p. Similar logic here. So m sub 2 is equal to square root of a sub 1, a sub 5. We then get the geometric mean between a sub 1 and m sub 2. Again, similar logic as earlier. Excuse me. Recall m sub 2 is equal to square root of a sub 1 times a sub 5. So now we are going to see if the logic is really similar to earlier. So there you have a sub 1 times the square root of a sub 1, a sub 5, and a sub 5 times the square root of a sub 1, a sub 5. Place the a sub 1 inside, a sub 5 inside. Addition of exponents when you multiply the same bases. That's a law of exponents. And since we can rewrite this as an exponent, 1/2, 1/2, and then you're basically multiplying exponents. 1/2 times 1/2 would be 1/4. So we are basically getting the fourth roots here. So m sub 1 would then be the fourth root of the cube of the product of the cube of a sub 1 and a sub 5. And m sub 3 would be the fourth root of a sub 1 times the cube of a sub 5. We can rewrite m sub 2 is equal to fourth root of a sub 1 squared times a sub 5 squared. Observe the exponents of a sub 5 always equal p, and the indices and the sum of the exponents of a sub 1 and a sub 5 always equal q plus 1. So again, we see a very similar logic to arithmetic. Again, get the equation for the coefficient of a sub 1, then we find it's q minus p plus 1. Again, that was exponent, not coefficient, if I said coefficient earlier. Either way, we're working with a similar logic to arithmetic's means. So from what we observed in the previous examples, the general formula for getting the pth geometric mean when inserting q geometric means between a sub 1 and a sub n is, there you have it. M sub p is equal to the q plus 1th root of the product of a sub 1 raised to q minus p plus 1 and a sub n raised to p. Similar logic to, again, we compare that to the arithmetic, and similar logic lies in additions in arithmetic became multiplications in geometric, multiplications in arithmetic became exponentiations, as you can see here, in geometric, and divisions became radicals in geometric. Then we get to harmonic means. So we are given two terms, 1 over a sub 1 and 1 over a sub n, where a sub 1 and a sub n form part of an arithmetic sequence, and a sub n is equal to a sub 1 plus quantity n minus 1d. We prove the base case of inserting a harmonic mean between those two terms. This will follow similar but slightly different logic to the arithmetic means. Get the harmonic mean of a sub 1 and a sub 3. We first add them and divide by 2. Notice how we put 1 over m sub 1 here, as again similar to an arithmetic sequence, but everything is in reciprocal. Add those two fractions together, simplify that complex fraction, then we get the reciprocal to get the harmonic mean. So 1 over m sub 1 is equal to a sub 3 plus a sub 1 all over 2a sub 1 a sub 3. Flip it around, get its reciprocal, you get 2a sub 1 a sub 3 all over a sub 3 plus a sub 1. Then, still similar logic, define q. The sequence has n terms, left with q if we remove a sub 1 a sub n. However, the denominator in the arithmetic sequence has now become a numerator and a coefficient. In this case, the coefficient of the product of a sub 1 and a sub n, which was 2 in the earlier example. Since we inserted one mean, q plus 1, 2. Again, we define p, and again, we'll see inserting 3 harmonic means. I don't know why that still reads arithmetic when it's actually harmonic, but the logic should be similar. We first get the harmonic mean between a sub 1 and a sub 5, second out of 3 means. So we have m sub 2 is equal to 2a sub 1 a sub 5 all over a sub 5 plus a sub 1. We then get the arithmetic mean between a sub 1 and m sub 2 to get m sub 1. And we get the that's harmonic, not arithmetic. And m sub 2 and a sub 5 to get m sub 3. Recall that m sub 2 is equal to 2 a sub 1 a sub 5 all over a sub 5 plus a sub 1. So there you have it. So 1 m sub 1. You can pause the video here if you want to see how the process actually works. But important thing is we get m sub 1 is equal to 4a sub 1 a sub 5 all over 3a sub 5 plus a sub 1. And m sub 3 would be equal to 4a sub 1 a sub 5 all over a sub 5 plus 3a sub 1. Now, we can rewrite m sub 2 is equal to 4a sub 1 a sub 5 all over 2a sub 5 plus 2a sub 1, and then observe the coefficients of a sub 1 now always equal p, and the coefficients of a sub 1 a sub 5 in the numerator, and the sum of the coefficients of a sub 1 and a sub 5 in the denominator are always equal to q plus 1. We observed earlier that the numerator was always 4a sub 1 a sub 5, And down here we had 3a sub 5 plus 3 plus 1, 2 plus 2, 1 plus 3, all equal 4, which is one more than the number of means we inserted. We then get the equation where x is the unknown coefficient of a sub n, similar logic to earlier. So a sub n's coefficient would always equal q minus p plus 1. So from what we observed in the previous examples, the general formula for getting the pth harmonic mean when inserting q harmonic means between a sub 1 and a sub n is... there you have it. M sub p is equal to the product of quantity q plus 1 times a sub 1, a sub n. I know that sounded quite redundant. All over quantity q minus p plus 1 times a sub n plus b a sub 1. Quod erat demonstrandum, or end of the proof.